All right. Okay, my friends, let's get started. Shall we? All right. Okay, welcome back. What is going on? Where are the people? What is that? Career fair. Okay. So why aren't you guys in the career fair? What's that? It's like you prefer the class or the career fair? I don't believe that, but it's fun. So how long is it? Does it take? Till 5 p.m. So you guys attended some of it at least, right? Everyone here. Like, if you haven't attended, if you want to go, you can go. It's fine. I'm not gonna. No hard feelings, right? If it's something for the best of your interest in career and all these kind of things, if you want, it's fine. Yeah, I will understand it. But anyway, last time we talked about query processing. We had this really interesting exercise about the two strategies to run the query in a distributed system, right? Yeah, it's strategy 1, strategy 2, and we went through a lot of details of how to calculate the cost. Again, the cost that we calculated last time was not like the exact cost, but it's kind of a rough estimate because there are more factors to the total cost of a plane, okay? But you guys like based this rough estimate, like you all came up with the cost of each step, and we figured that one plan can be the cost of one plane can be drastically higher than the cost of the other plane. And in these cases, if the optimizer, which is the component, the database system that selects what the best query execution plane, if it selects that high cost query execution plane all the time, for instance, that will be like a huge loss to the system because we use more resources to answer these kind of queries, and also to the user because the user it will lead to a lot of latency in the application accessing the database or using that query. So the user will also not be satisfied. So it's a loss in both sides. Okay, so this is just to motivate. We use that to motivate how is it different between, and we said in a centralized database system, even though we use the same exact plan in a distributed system, it was actually way worse than the other plan, even though that was the optimal in the centralized system. So in a distributed query processing engine, these are usually the steps. This schematic here will give you the exact steps that the query goes through since the time the user issued the query in the SQL language, for instance, and it goes through these steps or these phases. So you have the first step is called the global decomposition, and this is some of the steps in the global decomposition or the query decomposition is similar to what's happening in a centralized database system. It's not different, okay? And then once the idea here is that you take the query and you transform it into an algebraic form. Algebraic form, when we talk about relational algebra here, if we're talking about SQL. Okay, so this is a low-level operational language as compared to the high-level SQL language. And you impose these algebraic formulas on the distributed relations. So again, the assumption is that we have done fragmentation, we have distributed relations across sites over the network, and you impose these algebraic formulas on the distributed relations. Once you do that, the next step is to how can I localize these algebraic operators on local partitions or local fragments of the data. Okay, so this step is called the data localization, is that you localize the operations on the local fragments. Okay, and then after that, you do something called global optimization. So this is like an optimization step that take these local fragments and try to decide how to run the query, orchestrate the query, best query execution engine across these global, these kind of localized query fragments. And then you have local optimization, is that once you decide the global query execution engine, you send each local site, ask them to do a specific task that will contribute to the query answer eventually. So each local query optimizer also has a say in how to do things locally on that machine. Okay? So you go through different, like you go through two levels of optimization. One is global optimization, and the other one is local optimization, where each site decides how to run the query or this sub-query, part of the query locally. Okay, so again, so as we said, decomposition is same as in the centralized system. So what do we mean by this? So you have the query language, which is the SQL query language, and you transform this into relational algebra over the relation that you have. So assume you have two relations like this, R and S, okay? And these are, you're basically doing the join on R and S, two tables, and you're applying this, these kind of constraints in the where clause. Forget about the semantic meaning of this, but it's just a join between two tables, and you do kind of selection on the either the join predicate or selection predicate on either relations that you're joining. Okay. So as you can see, transforming this SQL query into an algebraic form like this is relational algebra. Down there is relational algebra. So you have two relations R and S, like here. This is the symbol for a join. And then on top of this join, after you join the two, you do a selection, and the selection gets the condition in the where clause, but in a conjunctive normal form. Okay? So this is exactly similar to that, but in a conjunctive normal form. And then on top of that, you have the projection, which is select what attributes you want in both after you do the join. So select projection A and C. So you guys, if you've taken a centralized database system course before, or database system course before, you may know what that means. Okay, I explain it briefly now, but most of you may already know what these operators mean. So this is relational algebra, and it performs the same exact task as this SQL query. So the query decomposition transformed the SQL query into relational algebra. So the question is, why we transform a SQL query into relational algebra? This is a question to you guys. Like, remind me why we do that, even in a centralized database system. Anyone? Please. Explain more. Yeah, please. Language independent. What do you mean by that? You're close. You're close. So you wanted to say something in the back, or?
I had another point. It's to optimize the query clearer. You can really range joins and selections.
Yes. So you're also very close, actually. So the SQL query language, if you look at it, does it tell you anything about what sequence of operations I'm going to do to process this query, or no? SQL. How many of you think it tells you something about the sequence of operations you need to do? Okay. 2. So, or few. So how many of you think it does not tell you any information about the sequence of operations to run this query? Okay. Also few. So what about the rest of the people, right? What are you hesitant? Okay. So it is the people who think that it does not tell you anything about the sequence of operations this is the correct answer. Why is that? Look at this. So here, basically, this is why SQL is called a declarative language. Declarative means that the user, the person who's using, or the application using the system, just says in that declarative language, SQL, what it needs from the data. It says what, it doesn't say how to get this data from the database. Okay? So it says, you know what, from these two tables, I want to join them together and filter things in these two tables that way, right? So it tells you what the system or the user says it in a declarative language, what the user wants, what. It answers the what. This is why it's declarative. Okay? Relational algebra is not a declarative language, even though it maps to the same thing. You might think it's the same thing. It's not the same thing. It is an operational language, right? What does that mean? It actually dictates the sequence of operations that your flow of data goes in. So here you can tell, yes, I start from the two relations, R and S. I did the join first, and then I did the selection that way, and then I did the projection. So there's a sequence of operation. So it is, you have one SQL query, and you might have different relational algebra formulas for the same exact SQL query. Okay? Why? Because this is declarative, this is operational. That's the main difference. And again, as the gentleman mentioned here, is that since you have one declarative, the query written in declarative language is just one query, and you might have multiple relational algebra forms that represent the same exact query, this means there is room for optimization, right? How can I have this different? Instead of doing the join first, I will push this, I will do the selections on R and selection on S first, and then do the join on the result. It is a different relational algebra form for the same exact SQL query. And this is one way of optimizing the query. This is the idea of the query optimization, right? I hope that makes sense to you guys, right? So that's exactly the difference between SQL and relational algebra. They're not the same thing. Also, that's just, as we mentioned, that also that makes SQL a powerful language to use. Why? Because you as a user, you don't have to think about the process of the sequence of operations. It just says what you want. So it makes it very powerful. All right, so this is basically the idea of what we have here. So again, the composition just takes this SQL query and then transform it into this algebraic form. Okay. And you also sometimes need to detect invalid expressions. So if you have this query, you know that A is not an attribute of R, so you need to detect that. This also happens in, so this happens also in centralized database systems. So there's no much different here. And also eliminates redundancy. The redundancy, and again, since you transform this into conjunctive normal form, you can do a lot of predicate logic rules here to impose these rules on, because it makes sense. So this one doesn't make sense, right? So, and this one can be actually reduced, can imply the other one. So it it's these simple things you can do in the query decomposition. And also common sub-expressions. So here, if the query leads to this relational algebra form, you have here the same selection condition on R on both branches of the relational algebra tree. So in this case, you just combine them together, right? That's also one thing that this exact module does. Algebraic rewriting. So you have a condition here, condition on the join. Maybe this condition can be split into multiple conditions, selection conditions, and pushed down. And we said that just a few minutes ago. So this is basically what the query decomposition does. So after decomposition, you have more than like the algebra, query algebra tree, relational algebra tree, and then you need to do the localization step. The localization, you have a relational algebra tree, but it's done on the relations. It's not imposed on the fragments of the relations. The localization step basically takes that relational algebra and impose it on the fragments. Okay, and again, you might have multiple relational algebra forms. Okay, so you want to take these and impose them on the fragments. Okay. So the localization step is actually pretty easy. So you start with the query, okay? Again, the algebra tree that you have. And for the same tree that you got, you directly replace the fragments with, the relation with the fragments that this relation constitute. Okay? But to replace them, that means that you have to replace them with a union operator. Because these fragments, if you union them together, okay, if you have a horizontal fragmentation, if you union them together, you will get the original relation. So you need to have R1, R2 till Rn, these are the fragments, union together. Okay, so this is how basically you replace them. And after you do that, you push this union. If there is any union, you push all of them up in the relational algebra. And if you have any projection or selection, you push them down to close to the relations or the fragments that they represent. And after you do that, you eliminate the unnecessary operations. What is an example? Let's take a look at examples. It's very easy when you look at the example. So again, so assume you have, this is a fragment, and you have, this is the condition that this fragment represent. Like if it's a horizontal fragmentation, it represents the range, like you did in your assignment, a range partition. And then conditions, it's tuple satisfied. Yeah, that's the condition. That's the range partition, for instance. So if you have the query, one of the relational algebra trees of that query is very simple like this. You have a relation R, or this is a table, and you basically want to impose selection, and the condition on the selection is E equal 3. The attribute E is equal 3. Very simple selection, right? Let's assume you have two fragments of this relation R, R1 and R2. R1 has the E less than 10, all the tuples with E less than 10. R2 has all the tuples with E larger than or equal 10, as stated here. So how can we do the localization in this case? Any ideas, please? Replace R with R1. What about R2? We need to, if we follow the localization steps that we did. R1 union R2. As simple as this, right? Exactly. Perfect. So you have R1 union R2, and then you do the selection on that. You've done with the localization? Not yet, but that's one step in the localization. The second step after you do that is to push the union up and then push the selection down. So the selection, you have E equal 3, E equal 3 here, and then the union up. This will return the same exact answer for the query. The question is, do you notice anything wrong in this? What is it? In the second part, the second branch, we don't have e equal 3. So this selection predicate is actually unnecessary. It's an unnecessary operation. So in this case, what do? That's the last step of the localization, is remove unnecessary operations. So eventually, you remove that because this return empty set. Eventually, localization will lead to just that. So it's a selection on only R1. You might, in the beginning, you might have seen that. You think it's easy, but the algorithm needs to go through these formal steps. If you have a very complex query, you cannot easily spot it with your eye, right? So these exact steps will lead you to the correct localization. Am I making sense? It's very simple. So to get to that, there are rules. So these rules are actually logic rules. It's a mix of logic and relational algebra. That's the first rule we've seen of removing the unnecessary operation. If the operation leads to an empty set, okay, that's an unnecessary operation. You remove this branch of the tree altogether. And that's what happened in the example we have. So we had selection e equal 3 on R2, e larger than or equal 10. This implies that you actually transform it into this, and this conjunctive form, if you impose it on the fragment, it will lead to an empty set. It will lead to R2 false, which lead to empty set. So very simple. This is actually what the algorithm does internally. Okay, so what about if you have a join like this and you have A is a common attribute between R and S, and let's assume you have these fragments. So these fragments are, you have R1, R2, R3, and only 2 fragments for S, S1 and S2. And again, they're partitioned based on the A attribute. So different ranges, A less than 5, between 5 and 10, larger than 10, and here less than 5, larger than or equal 5. And we want to join these two. And we have this, one of the relational algebra trees for the query was this. How can we do it? We follow again, it's not obvious in the beginning. So we follow the localization step. The first step is you bring the fragments and you do the union across them. Exactly. So for R, we got them all, we did the union. For S, we did the union, and then the join is already there. Next step is push the join down, right? So how can we do that? When we push the join down, how will this happen? Remember, we're joining R and S. Please.
Join R1 and S1, then join R2, R3, and S2.
And then on the other hand, you do the same, right? Yeah. Exactly. So you take for each one of them, for each pair of R and S fragments, you put them together and you join. And then at the end, you do a union between all of these. Do you see any problem with this? Any problem with that? Okay, any problem here? In this join?
It's united.
It's what?
United.
Invalid operation Y.
Plus the first one says A less than 5.
And the other one is A larger than or equal 5. So this means this will never lead to anything, right? Because 2 different values of A, and you're joining on A. Okay, so what about here? Same? If you spot it anywhere else? Where? This one? Exactly. So as you can see, you spot this and you figure that all of these are unnecessary operations. So the next step is to remove the unnecessary operation, and at the end, this is how it's going to look like. So you localize to the fragments, you did the join, and then you union everything at the end. So this is also another rule for the join we did here. So this is just theoretically how it happened, right? So the idea is that you always try to push the condition in the conjunctive form, and if this conjunctive form lead to false, this means that the whole fragment will be an empty set. And this is what we're trying to reach at the end. So if it leads to that, the algorithm will decide this is an unnecessary operation, and it makes perfect sense for sure, and then we'll remove this operation. Okay, so far we've seen how we do localization with horizontal fragmentation. What is the other kind of fragmentation we talked about? Yeah, before vertical, there are two types of horizontal fragmentation. Primary and derived horizontal fragmentation. Do you guys remember what the derived horizontal fragmentation is? Nobody knows? Okay. I'm sad. Yeah. Okay, let me remind you. Derived horizontal fragmentation is where you have a link, and the link between an owner and a member. You partition or you fragment the member in the relation, which member relation, based on an attribute in the owner. So, which means in order to come up with fragments for the members, you need to fragment the owner first, logically, and get these logical fragments, apply it on the members. Remember when we had the example of the pay and employee, and we want to fragment the employee table based on their pay, and the pay is in a different table? Pay was the owner, employee was the member, right? That's what we mean by derived horizontal fragmentation. So if we have that, so how can we do the fragmentation? So you have R1 and R2, these are the two fragments. In S1 and S2, these are the fragments in S1 and S2. So given that, so how can you do localization? You follow the same steps. So you already have the union here, so you push the union up, and you do the join down there between the couples, between the pairs. And then eventually, you will have it like this. So it actually, if you apply the same exact algorithm, you will reach a good. You will do the localization normally. There is no problem. However, in the case of derived horizontal fragmentation, the fragmentation is done based on a different attribute. This is why you have an extra condition here, and you have to check that in the logical expression that you do. So this is what we did, and it led to, we actually removed all the pairs of joins that led to also empty set. Okay, vertical fragmentation. How can we do localization with vertical fragmentation? So again, you have a very simple projection here, and you have two fragments, R1 and R2. R1 has AB and R2 has CD. So follow the same algorithm, okay? You do R1, R2, but in the vertical fragmentation, instead of a union, you have a join. You understand why, right? This is the reconstruction operator. So here you have a join. In this case, you have the join, you push the projection down the join. The projection be based on KA and KA, because we need the final projection needs to be on A. And one of them is not actually needed. Why is that? Because it doesn't have A. So basically the final will be a projection on only R1. So you guys understand the idea now, and there is of course like a logical rule for that. It also follows the same exact logic. Please.
Could you go over the vertical fragmentation again?
Okay.
Could you go through the steps again?
Okay.
Could you explain? I didn't get this.
Okay, so you start from, you have two fragments, vertical fragments, R1 and R2. Initially, you didn't have, like you had the relation algebra on R, right? In order to replace R with R1 and R2, you need to bring R1 and R2 and then do a join based on the key attribute. Because all of this, starting from here down, from this join down, this is basically R. So this is how we replaced it. And once you do that, you push this projection, you push it down to R1 and R2. But pushing it down, you need also to push down the K, which is the key. All right? Why is that? Because this is necessary for the join, right? If you don't have it, you cannot do the join. And then once you do that, you realize that this branch is not necessary because there is no A in R2. There is, again, we explained there is a rule for that, logical rule. And then you replace it, you remove it altogether. As simple as this. And again, once you remove that branch, this join is nothing because join it's a binary operation. So if there's this branch does not exist, this means the join does not exist. Better now?
Yeah.
Good. All right. Hybrid fragmentation. It's the same. Actually, if you apply the same algorithm, it's the same. So assume you have R1, R2, R3, and R1 is basically, it has vertical and horizontal fragmentation, the same for R2. R3 is just a vertical fragment. So you have this kind of fragmentation done on both on R. So if you have a query that has a projection and a selection, you go through the same kind of operations, and you will figure out that's the final answer. You go through the same decomposition algorithm, right? You figure that only you need to do this on R1. You don't need R2 and R3 because they either don't have the selection or the projection condition. So, and this is how the localization, the query localization works. Does it make sense to you guys? I think it's very straightforward. I tried to give more examples to make sure that you guys can understand. After that, once you did the query decomposition, you came up with a bunch of or a variety of relational algebra forms that can represent this query, the SQL, right? So let's assume you have 10. You take those 10 and you do localization on them. After that, you need to decide which one is better. So which means you need to do some sort of optimization, query optimization. And the query optimizer will decide which relational algebra tree is the most efficient after you do the localization on it, the most efficient to run this query. So, optimization. This is a huge, optimization is actually a huge topic. There's a lot to talk about in optimization. And in the database system literature in general, optimization was a really important topic. So, do you guys, just speaking of which, I like to talk about history sometimes. Do you know when we started using a database system? Like in the world started to use a real database system. What is that? 1980? No. Go earlier than that. The first database system please.
1940.
I'll go a little later. It's not that old. Yeah. It's in between. So it's in the 60s. Okay. So, by the first person who actually gave us the first system that we can call a database system. His name is Charles Backman, and he invented something called the integrated data store. So it was the first ever database system as opposed to file systems, okay? So it's the first system that actually have query functionality, there is a data model, and you can actually query the data model and do all these kind of things. So initially, he didn't have much optimization in the system, but he had a query language, he had a data model, he had all these kind of things, right? So that was in the 60s. And back then we didn't have that. There was no something called relational algebra, relational model, nothing of that whatsoever. So that relational model was invented by anyone? And by the way, Charles Backman took the Turing Award for inventing the new database system. So, and the relational algebra came in not so long after. So it was in the 70s, early 70s, by a person, should all know him. It's called Ted Codd, right? And there's a paper about the relational model. So this paper is very, of course, it's like one of the very most famous papers in computer science because relational model is used everywhere now. So he came up with the relational model and the relational algebra as the language to query relations, and also before that time, like the early 70s, we didn't have any relational model. People have database systems, but no tables, no relations, no relational algebra, nothing of that whatsoever. So he defined the theory behind relational algebra. So you see the relational algebra trees that we were explaining and all these kind of things, that's the guy who started that. And he also took the Turing Award for also this invention, right? You guys know what the Turing Award is? Good. Yeah, it's like, yeah, that's good. Yeah. Hopefully some of you will get it someday. Yeah. So that's it's just, I'm using this like to give you a little bit of perspective of what relational algebra. And since relational algebra and the relational model was there, companies started to working because they thought there is a huge value in database systems and specifically the relational model. And one of the very first companies that started building database systems that are very similar to what we see today, it was in the 70s, and it was a company. No, not Oracle. It's a giant. IBM, right? Yeah. So IBM is actually one of the very first, I will say the very first company to start working on a relational database system. And hence, they are the team that worked at IBM back then are the very first team that worked on query optimization. We're talking about query optimization. And a lot of the techniques I'm going to explain to you have been actually invented by people working in that company 30 years ago, or more even, like 30 to 40 years ago. So, and then Oracle came in the 80s. Yeah. Oracle came in the 80s, and then they did a lot of good work, and they have a great system for sure. And then you have Microsoft started to work on the business in the late 90s, right? And they have a big share of the market now too. So just giving you a little bit of perspective. And since IBM started working on, again, building relational database system, query optimization has been a very important topic. And there's been a lot of research on this in the 70s, 80s, 90s, and till today, there is still people working on query optimization. But the systems that you have, you guys are using Postgres, right? So Postgres, a lot of the optimization techniques are actually invented by people from IBM and later on Oracle, Microsoft and stuff. Yeah. All right, so what is query optimization again? Query optimization, there are so many ways to run the query. What is the best way to do? So it's an optimization problem as a generic optimization problem in computer science or operations research or anything. So you have different parameters and you have several optimization criteria. Sometimes it's a multi-optimization criteria, right? So if you model it from an optimization perspective, it is a very hard problem. So the optimization criteria can be different things. Can be you have you want to reduce the response time of the query, which is the time the user issued the query between this time and the time the user gets the answer for the query. That's the response time. So maybe you want to minimize that. Get the best plan that minimizes this criteria. Or maybe not. Maybe you have a lot of system resources, and system resources are expensive, and you want to minimize the amount of resources to use to answer the query. Okay? So would minimizing the system resources lead to a good response time? Sometimes, sometimes not. To get a good response time, should I minimize the system resources? What resource is the one that I need to really do the optimization on? In centralized database system for so long, since I gave you the history, people since the 70s till I'll say like the mid 2000s have been optimizing database systems for pretty much one simple criteria, one simple system resource. Can you guys guess?
Memory.
Disk, right. So I/O. Why is that? Data is usually used to be stored in a secondary storage. Because it's persistent, we need to have it on disk. Back then we had something called tapes. I believe your generation never heard of that, never seen something like this, right? So, but you've heard of hard disks, right? In 10 years, some people will never hear of hard because all the laptops, all computers now have SSDs in them and stuff. But you guys know of hard disks. So hard disks, it used to be a huge bottleneck when running a query because the data is stored on the hard disk, and getting the data, one page from the hard disk, one page that has data, that has like tuples that exist in a table, it's actually 3 orders of magnitude slower than reading the same page in memory or do processing on it in memory. 3 orders of magnitude, I mean like 1,000 times, sometimes more. So if you have to do something in memory in 1 millisecond, on disk you will do it in, like read it in, what, a second. So it's a huge difference in performance. And this is why query optimization strategies, when people consider that in the past, they always think, okay, how many pages I'm reading from disk? And if I can minimize that, I can actually get the best query plan. And I'll totally ignore, or pretty much ignore, CPU cost and memory cost, because it's basically nothing as compared to the audio. Does it make sense to you? So classic query optimization techniques used to optimize for the I/O as the main system parameter to optimize for. Fast forward to, I'll say, the late 2000s, we have systems that become different. I'm talking about computer systems. So back then, we used to store the data on disk for several reasons. One reason is that it's a safe place for the data to be, because the RAM is volatile, right? So once data is not persistent in the RAM. Okay, that's one reason. The second reason, okay, so someone can ask, okay, I will have a version of the data saved on disk, but I will load it all in memory and then have the database work on everything in the RAM. It's a good solution, but back then was not possible. Because back then, memory was a very scarce resource, very expensive. And the hardware technology for computer systems we didn't have good technology to support large RAM size. I remember like the first computer I worked on as a kid, it didn't have, like it had nothing. If I told you, you will laugh about it or something like this, yeah. The amount of RAM in it. So, and now, what is the biggest, like your laptop, like I believe at least has 8 GB RAM or something like this. And you'll have like, when you say to someone who's like, man, I have a poor laptop, right? It's like, I wish I could have more. So we didn't have that back then, right? And some of you may remember this as well. So hardware technology was very limited. So this means we dealt with memory as a scarce resource. So that means we have to store everything on disk, and we load necessary data for the query in memory when we have the query that needs this data. Otherwise, it's safe on disk, and we load it when necessary. But in the late 2000s, we had hardware technology has become better. So people like hardware manufacturers like Intel, a lot of other companies. Now we can have, like what is the maximum amount of RAM we can have? The last time I've seen it was 2 terabytes or something like this. I'm not sure the hardware technology can get even better, right? So 2 terabytes is easy. You can buy a server now that has 2 terabytes. If you have a startup, you have a few $1,000, you can buy 2 terabyte RAM, which is amazing, right? So 2 terabyte is huge. And if you're talking about a lot of the database applications are what? Banks, library, flight reservation, the classic database applications, all of them at most are 1 terabyte. So you can load the whole database in memory very easily, the whole database. Which means that the bottleneck of the hard disk is not an issue anymore. In that case, if you have in-memory databases. So what is the bottleneck then? Bottleneck is totally different things that people didn't think about in the past. Like people now, okay, granted when I store it in memory it's way faster than disk, but can I make it even better? So there's a lot of research going on now on how to optimize database systems for data stored in memory as compared to, so query optimization will change, query processing will change, we'll talk about that later in this lesson, I'm just giving you an overview. This is for in-memory, so also when we have distributed systems, there are other factors that are more important or equally important as disk. What are these? Network, yeah. Communication costs. So data that is transferred across the network. This is a huge cost. So back then again, and so the optimizer needs to take into account that. And we've seen example last time about the tuple transfer cost, and you guys did a great job actually figuring out the cost. So if the communication cost is really high, this will affect the query optimizer. Query optimizer has to decide whether this plan or the other plan based on the communication costs. Is the I/O cost more than the communication cost? Or it depends on the network technology, depends on the secondary storage technology. If using SSDs is different than disks. So there's a lot of factors that the query optimizer needs to take into account. So as you can see, it's a very complex task. It's not a very easy task. So people have been working on this for so long, but here are the basic idea behind it. So you have an input query coming to you, and the input query, again, you have multiple of these relational algebra trees, so you have a search space. So you generate a search space, and in this search space, you find a query execution plan. You have a search strategy in that search space that will find the best query execution plan using a cost model, and based on the search strategy you get and the cost model, you get the best query execution plan. So this is the optimization problem we're solving. Very classic optimization problem. So what is a search space? Again, search space is the different relational algebra trees that can be used to run the query, the same SQL query. So it's a different sequence of operations, different organization of the operations, return the same result, but it's different. It has different costs. Okay? So this is the search space we have. So questions for you, like a question for you guys. If we have n relations, okay? So what is the order, what is the complexity of the search space, the size of the search space? 2 to the power n. Why is that?
For each,
The y2. That's my... yeah.
for each operation, we will have
You have n relations. For every single relation, there are n minus 1 ways to organize the other relations, right? So what does that mean? It's in the same order, it's exponential, but it's n factorial. Okay? So it's still exponential, so it's the same order, but the real number is n factorial. So any exponential search space is definitely something that we've learned in algorithms, and if you take in algorithms and data structures, we want to avoid that. This is a very hard problem. So you have n relations, you have n factorial, like order n factorial equivalent join trees. Join trees mean relational algebra trees. Why we say join trees? Because join is the most difficult problem. The join order, which can I join A with B first and then do the C, or A C first and then B? So it makes the problem more complicated. So the question, okay, this exponential search space is impossible to search, or it is possible, but you cannot get it in polynomial time, right? You can get to the optimal answer. So how can you, the first very simple idea is how to reduce the search space. So any ideas how to reduce the search space? Please. Heuristics. So what kind of heuristics you think of?
previous search times, network latency times and stuff.
Yeah, no, based on relational algebra. Heuristics based on relational algebra. Please. Push down selection and projection. Exactly. So that's one idea. Why is that? Because you reduce the size of the data, intermediate results, right? And as long as you reduce the flow of the data up, it's better, right? So that's one heuristic. Even though it may not always lead to the optimal plan, but it usually gets you a good plan. Another thing people used to do is something called the linear join tree. What does it mean? These two join trees are possible to be enumerated in the search space. But in the past, people totally avoided the bushy join tree, the join tree that is balanced like this. And they always the search space, they only enumerate the linear join tree, or the left deep tree. Why is that?
Use indexes of the left part of the tree.
Yes. So there are one reasons. First of all, this is not going to be very useful if you don't have a parallel system. Because if you come up with this, it may be useful in a parallel system, but usually you need to, if you have a centralized system, you have to do R1, R2, and then join the result with something else. So this is why people avoided that in the past. But in a parallel system, this needs to be considered. So other heuristics needs to be taken into account. So this is the search space and how you reduce this. People used to reduce the search space in the past. Postgres used the linear join tree. MySQL does not enumerate this. It reduces search space by enumerating only the left deep tree. Okay? So this is search space. Next is, okay, now I reduce the search space a little bit using heuristics. So how can I move in the search space to find a good plan? So that's called the search strategy. So there are different ways, search algorithms, there are different ways to do that. You probably heard of these algorithms. So there is a deterministic algorithm. Deterministic means that algorithms like dynamic programming and greedy. So dynamic programming is basically you have, while you're moving in the search space, you memorize the states, okay? And you move in a deterministic way. You don't just move randomly in the search space. You move in a very deterministic way. You memorize the states, and based on that, you take decisions, okay, on optimality or not. Greedy is kind of the same. It's a different set of algorithms because you start with a greedy heuristic and move in the search space that way, but it's still very deterministic. There are other kind of algorithms called randomized algorithms. So randomized is basically you kind of, as if you do a sampling on the search space and you pick one plan at a time, you evaluate it and then move to another plan, evaluate it, move to another plan, randomly move in the search space. As if you've taken graphs before, you're familiar with the concept of random walk, right? It's the same, but it's a random walk in the search space. So example of that are actually simulated annealing. How many of you have heard of simulating annealing before? I'm amazed. This is good number of people, because in previous offerings of the class, nobody knows. I'm not going to ask you in the exam about simulating annealing, but just if you've taken CSE 510, you should have already known that. Or you've taken optimization or algorithms, you should know what simulating annealing. It's basically it's a randomized algorithm that help you search in the find an optimal solution in the search space, but using again a random walk or randomized way. To give you an idea what I mean, difference between deterministic and randomized. Deterministic, basically, you start from the two relations and you keep adding up in the plan like this. And again, this is like dynamic programming. So you start from a small and then you keep moving to a different state. You memorize it, the cost of it, and you keep moving on that way till you construct the plan that you want or you reach an optimal solution. Randomized, no. Randomized, you start with chunks, with big plans, and then you keep moving randomly in the search space. Randomly, of course, with a criteria, okay, not just blindly. And again, randomized is better in terms of if you have a lot of relations that are being joined together. Randomized might be more efficient in terms of the time to find a good plan as compared to the deterministic. Running something like dynamic programming, for instance, it will like be a huge amount of time to get to the answer. So what is the cost of dynamic programming usually?
N squared.
N squared?
Polynomial.
Yeah, it's polynomial. Yeah. It's not exponential, so that's a good thing. Will this reach an optimal plan? No, it will not reach an optimal, because first we reduced the search space a lot. So we removed a lot of things that might have been the optimal plan. So dynamic programming, it will be a good solution. It will find a good plan. Or let me rephrase that. It will not get you the worst plan. Right? So if the plan, remember the last time the plan that has like 30,000 and the other one has 400, it will not get you the 30,000. It might get you one that is 600 instead of 400, the cost. But it's good enough. Okay, so how to calculate the total cost of a query execution plan? Again, in deterministic approaches, if you're doing dynamic programming, at each step, at each stage, you need to calculate the cost. Okay, and this cost is actually accumulate the cost to decide what plan is better in this search strategy. So how to calculate the cost? In a distributed system, the cost, as we mentioned, response time. So you have a total cost, CPU cost, I/O cost, and communication cost. CPU cost is basically number of instructions. You know CPU instructions. If you've taken computer organization before, you know what the instruction set and how each instruction works in the CPU. So the number of instructions multiplied by the unit instruction cost. Okay, the unit instruction cost is not the same for sure for every instruction. So every instruction might have a different cost, but this is just a simple way to look at the cost. And usually, the unit instruction cost, it's kind of a statistical distribution. of the cost of the instructions that the CPU has. And every CPU is different, and if you have a new hardware, of course you need to have a different cost for this. And then I/O cost, this is basically the unit disk I/O multiplied by the number of disk I/Os. How many pages you read, and you multiply this by the cost of reading one page. Communication costs, the number of messages you transmit in order to answer this query, times the transmission cost for each unit. So you can translate this into response time sometimes, but it doesn't always say, especially if you have a parallel distribution of the query, response time doesn't reflect directly, this does not reflect directly the response time. So what is the most important thing about calculating all these costs when you have a query algebra tree like this, relation algebra tree? The idea here, yes, now I know disk I/O, what is the cost of each reading a page? This is easy to know, right? Because you know the speed of your processor, the speed of your disk, hard disk, and all these kind of things. So it's easy to know. It's not like the biggest deal. But the biggest deal is sometimes when you're building this relational algebra tree, you have, like, for example, selection and then join and then another kind of selection and then join, something like this. The size of the intermediate results between different operations. How can you estimate that? Because if you know the size of the intermediate results, you can know how much CPU cost will that take to process, how much I/O cost will that take to process. But you don't know the size of it. How can you estimate the size of the intermediate results in between different operations in the query tree? How can you do that? Statistics on table, exactly. So if we can collect, the database system can collect statistics on all the relations stored in the database, we can use these statistics to calculate the size of the intermediate results. Simple thing. Let's assume we have a very simple query, like select from relation R. Just select and relation R. You want to read the relation R and select something from it. Very simple relational algebra, just one relational operator. How can I estimate the size of this operation or relational algebra form? If I don't know how many tuples exist in R, I cannot know the I/O cost. Because if I know how many tuples exist, how many pages are used to store R on disk, I can actually know how many pages I'm reading. And hence, I can estimate the cost. All right? What if you have a bigger plan? So once you select something, you need to, this selection has a predicate. You're not selecting everything from that table. You're selecting only, let's assume it's an employees table, and you're selecting where employee is equal, employee salary is larger than 3K. So these are not all. How can you know the size, how many tuples are actually represented by this predicate? You wouldn't know that unless you have statistics on the salary attribute, how it's distributed, okay, in this table. If you have a histogram that tells you, by the way, salary between 3K and 5K, we have 5,000 tuple represented by that. Between 10K and 15K, you have one tuple represented by that, something. So if you have these statistics, you can estimate the size of the intermediate results. And estimating the size of intermediate results will help us calculate all these costs. Am I making sense? Good. So this is why, as a gentleman mentioned back there, statistics is a very major component in a database system. So each database system has a set of statistics that it optimizes the query on. It uses these statistics to estimate the size of each step of the relational algebra formula, and based on that, calculate the whole cost of this query execution plan, the other query execution plan. And all of this is, of course, is fed into a cost model that will help us in the query execution search strategy that we talked about, either deterministic or optimized and randomized and all of this. So optimization statistics. I wanna just show you something. Can you guys see that? Okay. So this is like oh, it doesn't do it here. Okay, sorry. So this is a database. A little better. Okay. So this is basically a database, and in the database, it's I'm just saving a users table, and this is again pretty much from the same data that you're using for your assignment, but I'm just storing the user table. So let me just remember this. So as you can see, this is basically the schema. So you have user ID, age, gender, occupation. Occupation is a different table. Occupation means it's the occupation of the person, and the zip code. All right. So now if I want to understand what is the query execution plan when I did select from users, what is the query execution plan here? Do you guys have used Postgres? What can we do? Anybody knows? Anyone? Okay. I'm just going to do it. So there is something called explain analyze. Have anybody used it before? Okay. Before you do any query, you just write explain analyze, and then you say the same exact query. So what this explain analyze does in Postgres? It tells you two things. It tells you what is the physical execution plan, not even the relational algebra. It tells you how this query physically ran on disk and retrieved the data and everything. And it tells you the estimated time or estimated execution plan and the actual time that the query really ran in. So if you do that, down there, can you see? So here, wait a minute. So down here, it says sequential scan on users. So this is the plan that is selected to run the query. The query is basically a simple selection. Sequential scan means this is a physical operator that opens the file that has users on disk and does a sequential scan on all the tuples in that file. And for each one, it returns it. And this is the total runtime it took. And this is the estimated number of rows. This is the estimated rows of the query. So the query optimizer estimated to be 943 rows, and actually it estimated the same exact as what happened. All right? Let's do something. So if you do this, select from users where age equal 24. So I'm just selecting all the tuples that are age equal 24. And then I'm going to do explain, analyze, select from users where age equal 24. So again, you've done a sequential scan also, and it estimated 33 rows and it returned 30. So as you can see, this is a very very accurate statistics collection here because it estimated 33 rows and it actually returned 33 rows. What does it mean? This means that the statistics stored there used by the query optimizer are very accurate. Is it accurate all the time? No, because this is a very simple query on one table and there's not much in the equations here that you add. Let's take another query. So let's create an index, okay, on users. You create it on the age. So this is basically this command, create an index on the age. And run the same query again. What happened here? So you did, instead of a scan, you did something called index scan. Index scan is basically, instead of accessing the file directly, you access the index that I just created. So the query optimizer picked that plan, okay, instead of sequential scan. And once you did this index scan, you did an extra step here to filter the users based on their age, okay? So this is usually happening with the index. And the estimation here was 33 and 33 and everything was fine. As you can see, with the index, you have better query execution than without the index. So let's do something else along the same. So you have here users and doesn't make sense to you guys, right? So you understand what the query optimizer does in this case. So let's join the user with the occupation. So I want to select all the user. So users U with occupation O, where still the U.age is 24 and U dot, so what's it, like ID equal O dot ID, I guess, here also. Occupations, yeah. It's ID, okay. So I'm joining the users and the occupation to get the occupation of each user, okay? And I'm doing explain analyze. So what happened here is that the first step, it accessed the users, it did an index, used the index, and after that, it took the results, did a scan on the other side on the occupations, and the results of the scan and the index scan in the user, because we have an index on age, it joined the results. Okay, used an algorithm called hash join. All right, so this is basically the query optimizer. And let's see, the estimated number of rows was 5, but it actually returned, the actual is 2. So the estimation here was not very accurate. Why? Because it's more complex and we have intermediate results and it's more complicated, but it's close. It's not exact, but it's close. All right? So again, explain analyze is a good way to understand because it tells you how what the real exact execution plan that the system chose. Next time I'm going to tell you how this optimization works and how can we optimize. Thank you so much.